So before we start normal distribution, which is one of the distributions in standard statistical analysis, I just want to give you an idea about some key terminologies. And these are the parameter and then a statistic. What is a parameter? The parameter, which is usually represented by mu, okay, has to do with, let me just write it out, is represented by mu, has to do with a number that describes a data from the population. So if you take a population of students in this university, that population, if you should get the mean and the standard deviation from the entire population, these will be called parameters. But if out of this population, you sample a portion of the student, let's say students from the business school, you sample these students, and then you calculate an information such as the mean or the standard deviation from this, the same thing that you would have done with the population, they have different name, and this is known as a statistic. So a statistic describes the data from a sample, whereas a parameter describes the data from a population. A population is always larger than a sample. So keep that in mind. And some of the information you want from the population or from the sample. Now, why do you call it a sample in the first place? We call it a sample because we don't have all the population, or it's very difficult to get the entire population. That's why we take a sample. And some of the things we use to describe the sample include the mean, the median, the mode, the standard deviation, the kurtosis, the skewness, okay? And several other things, the range and the other things. So these are statistics that will explain the sample, the data from the sample. All right. So with that in mind, let's set ourselves going. So if you look at this table, if I take a sample and I calculate the mean is called X bar. But if I take a population and I calculate the mean is known as mu, the Greek letter mu. If I calculate the standard deviation from the sample, that statistic is known as sample standard deviation. And if I calculate a parameter from the population, standard deviation parameter from the population, this is known as the population standard deviation. Okay. So you want to know the difference between the two. Okay. Most of the time we'll be dealing with the sample, but we will hypothesize on the population. If you don't get this one, I can quickly explain, but I want you to have this in mind before we start. We start what? Before we start normal distribution. Now, every distribution we've looked at the binomial distribution. We've looked at the Poisson distribution. Okay. We've looked at other distribution. We are now going to look at the normal distribution. The binomial is used when we are dealing with only two possible outcomes. And this was a discrete, information that we are dealing with. But in real life, outcomes of random variables are not discrete. They are mostly continuous. Continuous means that they take on every value, okay? Every single value. So in real life, you deal with continuous random variables. And that is why we need to study probability distribution that deal with continuous random variables and not just discrete data sets. Why? Because many real life situations, psychological situations, educational situations, are approximately normally distributed. And I'll come and explain what a normal distribution is. So what are some of the things that are approximately normally distributed? You want to understand that the normal distribution was discovered by a German mathematician known as Carl Friedrich Gauss. And so the normal distribution is sometimes called a Gaussian distribution, the bell-shaped distribution. And we are going to understand why it is called the bell-shaped distribution like that. Why is it called a bell-shape? You're going to fully understand this. So from a long time, today the normal distribution is well known. Why? Because there are so many things in this world that are normally distributed. Give me some of the examples that are normally distributed. Who can give me one example of things that are normally distributed? You can type it in there. Tell me some of the things that you believe are normally distributed. You can give me one. Is there anything you know that is normally distributed? Type it there. Type it there. Type it there. That will give me an impression that you understand. All right. So Abbas says height. Mary says height. Rita says air. Emmanuel says gender. Emmanuel, gender is not normally distributed. Gender is binomial. Okay. Nyako and Sefako, you are all saying age. That is true. Okay. Now, if you are here and you are not typing some, okay, it means that you are way behind. So these are some of the things that are normally distributed. Income, money, test scores. For example, test scores. Okay. Test scores are normally distributed. The size of shoe. Most people's shoes are normally distributed. Blood pressure is normally distributed. The volume of things is normally distributed. The height and the weight are normally, in fact, so many things are normally distributed. That's why it's important to study normal distribution. Okay, now let me go back and explain to you why we say these things are normally distributed. So when we take a particular information like the test scores of students, okay? So let's say we have the test scores of students. And the test scores of students, we said, is normally distributed, right? Normally distributed. Good. Now, what does that mean? What it means is that, and the normal distribution, when you look at the normal distribution, the center, we are going to discuss it very soon, the center is the mean. So the mean or the middle gives you the position or the location of the distribution. That means that there is something deviating from the center. There is a deviation from the center. So as you start from the center and you start moving to the right, you are deviating. As you start moving to the left, you are deviating from the center. Okay. And this deviation is defined by the standard deviation. But why is it normally distributed? Why the word normal distribution? Because when you take, for example, the exam scores of most of you, you will notice that a few people will be having an A. So they will be at the top of the distribution. Another few people will have F. They will be at the bottom of the distribution. And then majority of the people are going to be in the middle. And that is why you see that the peak is at the middle. The peak is at the middle, which means that there's a lot of the information that is in the center. Few information are at the edge. But if the distribution had been something like this, okay, if it had been something like that, it means that majority of people are at the bottom of the distribution. And that will not be normally distributed. Okay. So normal distribution is what it is because majority of the information are around the mean, are within the location of the center. Okay, so several things. It's not only exam scores, ages, income, and several things are normally distributed. Now that begs the question, okay, that the shape of the distribution, this normal distribution, is a normal curve. And there's one key point you want to understand about this normal curve. When you look at this normal curve, because the mean is in the center, the entire area under the bell-shaped curve is set to be 100%. Okay, for example, you can always measure the area of a square, right? You can measure the area of a square. You can measure the area of a rectangle. Okay. Now, if we want to measure the area of the normal distribution, the entire area is 100%. Okay, so we know that. Now, you want to understand that even though the distribution towards the bottom, towards the edges, it looks like it's touching the axis. In reality, it never touches the axis. The distribution keeps going till infinity, okay? Till positive infinity on the right. And as you move to the left, till positive infinity on the left. Okay, so the area under the normal curve is 100%. What does that mean? What it means is that if I ask you to tell me half of this area, what number are you going to tell me if the area is 100%? And I tell you to give me the value for half of this area. And by the way, that area, which is 100%, is the probability. Okay, because probability is also within 100%. So if I tell you that I want you to tell me this shaded area, how many percent will you give me? You say 50%, exactly, Joanna, Princess, Rita. Okay, so that's what you are going to say. So our job now is to find the possible areas, in other words, a possible probability, okay, under this normal curve. What are the possible? For example, if I tell you that, okay, you were able to tell me the 50%, but what if I tell you that I want only this small portion here, just this small portion? How, what criteria can we use to get to that? For example, we know that these are the scores of students, right? We know this as a score. And then I tell you that the mean score was 70%, okay, or 70%. And now that's the mean score. And the deviation from the mean is in the order of maybe 10 standard deviation. So the 70% is the mean, okay, and the standard deviation from the population mean is 10. So that's the standard deviation. Okay, and then I tell you that I want you to be able to tell me, okay, what is the probability, which means that what is the area? What is the probability that if I pick a student at random, that student is in this shaded area? You can see that that shaded area is not 50%, because 50% is the whole of this area, the whole of it. Okay, and there's a portion here that is not part of the area. So you got to take away this area and take away that area, and that will get you the shaded area that we are dealing with. So how do we get that? How do we get that particular area? Now, first of all, if the mean is 70%, then it means that, and the standard deviation is 10. It means that as you move to the right, you are increasing the deviation by 10. And as you move to the left, you are reducing the deviation by 10. What does that mean? This is what it means. Okay, and just clear this and show. What it means is that if the mean is 70, then the next deviation, the next one standard deviation from the mean will be 80 on the right. The next standard deviation, which is 2 standard deviation from the mean, will be 90. Okay. And 3 standard deviation from the mean will be 100. Okay, and then keep going. And then 1 standard deviation from the mean to the left will be 60. 2 standard deviation from the mean to the left will be 70. Sorry, it will be 50. Okay, you are going down. And then the 3 standard deviation will be 40, and then on and on and on and on. So that is how, if I were to label the standard deviation, that is how it is really going to be. So how do we get that area? That is the essence of this whole course. Okay? How do we get the probability that if I pick it can be ages. Okay? If I say that, let me give you a typical example here. Okay? Just note that the mean is 0 at the standard level. I'm going to explain that before I explain. So here's the thing. Once you have age is in numbers. Income is also in monetary numbers. And kilograms is also in some kind of numerical numbers. There are some things that are measured in hundreds. There are some things that are measured in millions. There are some things that are measured in decimals and so many things. But these numbers are not standardized. Shoe sizes and salaries of income, the numbering are different because shoe size can be 42. Okay, shoe size can be 42. Okay, and the salary of a person can be 5,000. These 2 numbers are not standardized. But in their world, in the world of shoes, it's standardized. In the world of shoes, it's understandable. In the world of income, it's understandable. When you take kilograms, okay, kilograms will be in a different standard measures. So we need a kind of a standard measure for all these normal distribution, so that when I say this number can fit into any of the different, different applications of normal distribution. And what is that? Well, this has already been developed, and this is known as the standard normal distribution. The standard normal distribution. And that standard normal distribution, okay, the mean is 0 at all times. So this is the same thing, the same distribution, but I've now standardized it. The mean is 0, and anything away from the mean to the left or to the right will be the deviation. And that deviation is 1. So the standard deviation is 1 from the center, from the mean. So if I have the ages of people in a class, and let's say the ages are 34 years, the average age is 34 years. That 34 years is at the mean in terms of what? Ages. Suppose the standard deviation is 4 years. It means that anytime I move 4 steps, which is 38, okay, 4 steps, which is 42 to the right, that is what I'm going to have. But I can take these ages and standardize it into the standard normal distribution. And the mean, which is the 34 for the ages, will become 0. Okay, will become 0 for the standard normal distribution. And so the standard normal distribution has a beautiful job it does. And the job it does is that it helps you to be able to convert and approximate and measure the probability of anything. So 2 statistics that you should know about the sample. 1, the mean, the location, the position, the center. And 2, the skewness. The skewness is the spread of the data. It tells you how flat and how wide and normal, which one is flat and which one is flatter and which one is taller. All right, that's the distribution. Which one is flatter and which one is taller? Okay, so let's deal with a flatter. Is it the A or B? Which one is flatter? I'm getting some answers here. B is the flatter one. Okay, so if B is a flatter one, what does that tell you about the deviation? If B is a flatter one, it means that the deviation, the standard deviation is large. Okay. The standard deviation is large. So the standard deviation for the flatter one is large. The standard deviation for the taller one is small. So when this, remember, as you get closer, towards one, that is when you're having a very vertical standard deviation. So the standard deviation is smaller for a taller normal distribution. And if it is taller, you can see at the peak, that spread is measured by the standard deviation. And why is that so? Well, because the entire density of the bell-shaped curve is covered by 100%. So the whole of the density is 100%. Even though I told you that the edges will fall asymptotically, meaning that the edges act like they are getting to the axis, the horizontal axis, but they never touch the axis. Okay. So anytime you change the width, that is this one, the horizontal situation, that will also change the height. Okay. So as you try to stretch the width, the height will be reducing. As you try to close the width, the height will be increasing. And as you stretch and close it, that is the standard deviation. As you stretch it, okay, what you are doing is that you are increasing the standard deviation. As you close it, you are reducing the standard deviation, which means that you will have a very tall bell-shaped curve. All right, so keep these things in mind. And so when I take a particular data set, okay, called X, if I take a particular data set called X, okay, I have to know the mean and the standard deviation of the data set. I can say that the data set is normally distributed. We use a sign to indicate that the data set is normally distributed. That sign, there is a tilde sign, which means distributed. So it is distributed normally, capital N, with a zero mean and a constant standard deviation. Okay. So it is always having a mean and then a standard deviation. Anytime you want to know the distribution. By the way, we knew about this some time ago when we were looking at the previous distribution. So what is the essence? What do we really want to do? We've already indicated that the probability or the area under the normal curve is determined by the number of standard deviation that particular variable, whether it's age, height, scores of students, whether that particular, the number of standard deviation that particular age is from the mean. How far away the age, the money, the height, the scores is from the center, you can use that to determine the area under the bell-shaped curve. You can use that to determine the probability because the area is 100%, the probability is 100%. And I've already told you that because most things are normally distributed, but then they are not standardized, there is a standard normal variable called Z. And whenever you have that Z value, you can use that Z value to help you. Let me write it here. You can use a Z value to help you to get the probability or the area under the normal curve. So if I have a particular random variable X, say age, and I know the mean of that age, all right, I can convert that mean of that age and I'll be able to know its corresponding Z value. And once I know its corresponding Z value, now that Z value gives us the standard normalization. So now I can use that to get the probability or the area under the normal curve. Because the Z value has already been computed in tables. And these tables are existing already for you and I. Then we can use those tables to be able to arrange. Now, there is a formula where you can convert any random variable, whether it's age, height, volume, time, money, any random variable, you can convert that random variable as long as it's got a mean and a standard deviation. You can convert it to the standard normal Z variable using this formula. So this formula says that take the sample mean, subtract the population mean from it, and divide it by the standard deviation. That is a population standard deviation. Once you do that, you will get the Z equivalent of the variable that you are dealing with, the random variable. And then you can use that Z equivalent to arrive at anything. So let me give you a typical example of situation where you have different standard deviation, okay, and different means. So in the top graph here, you will notice that both of them have got the same mean, 100 and 100, the same population mean. But I told you that if the standard deviation is large, the bell-shaped curve becomes what? Flatter. So you can see that here, the standard deviation between this one and this one, the left one is large standard deviation. And because the left has a large standard deviation, you can see that the bell-shaped curve, the normal curve, is flatter compared to the one which has a lower standard deviation. Because that one, the bell-shaped curve, is more steeper, or it is taller. What about the mean? What if you change the standard deviation? What do you call it? You change the mean. All right. So the mean is now different. Remember here, between the top and the down here, the standard deviation is the same. All right. The standard deviation is the same between this top and down, but the means are different. There's a higher population mean for the bottom one. What does that mean? What it means is that it will be moving more towards the right. The mean, the peak is the top portion. The peak will be moving more towards the right than the one which has a lower population mean. That one, the lower you are, the more leftward your peak is going to be. The bigger you are for the mean, the more rightward that you're going to be. So just note these differences. Okay? Just note these differences. When you take your time a little bit, you'll be able to crack all of it. Yes, Aquile, you have a question.
Sir, please, I want you to please explain the difference between the mean, the one that is the U, and then the X, because I'm a little bit confused. If what I understand, you mean the U one is the mean at the top, and then the X is the sample mean.
No, the sample mean is rather X bar. That is not shown here.
Okay.
Now, let me get you, don't hang up. The sample mean is from one of the observations, the random variable. So let's say you have ages of 20, 30, 40, 45, and then 50, all right? And you want to find, each one of this is an X. Each one is a random variable. Each one is a random variable. Each one is an X. Now, if you find the mean of these numbers, that will give you X bar.
Okay.
Okay, but that is different from mu. Why? Because this 20, 40, 45, 50, it was taken from a certain population.
Okay.
And that population has got its own mean. And that is the mu here. But because you have taken a portion of the x's from that population, when you calculate the mean, that mean is obviously going to be different from the population mean, isn't it?
Yes, please.
And that mean is what we call the sample mean here.
Okay, thank you.
Yeah. So the sample mean is the mean of each of those random variables. Each of the random. So the x is any of the random variable. Any of them. 20 can be the x, 30 can be the x, and any of them can be. And from that, you calculate the mean. And that mean that you are hoping that that mean which you have calculated, which is the x bar, you are always hoping that that mean is equal to the population mean, but it's not. It's not, because the population is large. Some of them you don't even see. Okay. But you are hoping that that x bar, which is the sample mean, is closer to the population. Okay. I have another hand raised, and that is Freeman. All right, Freeman, you can raise your hand. Princess, you can lower.
All right, Doc, thank you. So in that case, with the previous slide, the formula for Z, shouldn't it be X bar minus mu instead of X minus mu?
Okay, so no, I've shown you the formula. It's not going to be X bar minus mu because you are not comparing the mean with the population. You are comparing a standard. So what you are trying to say is that there's a population mean already, okay, which is the mu, and then its standard deviation. And you are now going to now look through this entire population, and you are going to identify, suppose you close your eyes, and then you pick a particular age among the population of ages. What is the probability that that particular age, which is X I'm talking about here, what is the probability that that X is bigger than the mean, than the population mean? But what is the probability that that age is between 40 and 45? So you now have two X's. So don't bother about the mean. Don't bother about the sample mean, because the sample mean itself is obtained from individual random variables, which is the X's. So I would rather want to know the X before I know the mean of these X's. Okay. Please remember, you don't have the random variable. You don't have the random variable. You don't have the mean of the sample. You don't have the mean of the sample. Okay. But you know there's an entire population of sample. And so you want to identify a particular variable. If you have the mean, you can only get that mean when you have gotten individual random variables. So the mean is easy to calculate. There's normal sample mean is easy to calculate because all I have to do is to just add the individual random variables x together and then divide it by the sample size. Okay. But here you don't even have the sample size. You are not sampled. You haven't, but you know there is an existing population and you just want to know from that population what is happening. Okay. So that is how it's supposed to be. You don't have the sample size. Friedman, are you with me?
Yes, Doc, I get it now.
Perfect.
Right, thank you.
Now let's move on. And then when we get to a couple of examples, A is going to make clear sense. Tell you, it's going to make clear sense. So let's take an example. But before we move on, let's clarify some few things. So let's assume that, and this is a very quick example, because there's a rule that I'll need you to understand. Now let's assume that in a population of kilograms of bags of rice, you know, when people are going on the holiday, they will now give you 5, is it 5 kilogram rice they give, or 5.5? Is it 5 kilogram or 5.5? I don't know whether you got some last month. Did you get some 5 kilogram or 5.5 kilogram? Is it 5? 5.5? Okay, 5 kilogram, good, thank you. So now let's assume that it is 5.5 kilogram of rice, bag of rice, that is given out. And this is a population mean. So the mean kilogram of rice that you get, the population mean kilogram of rice that you get in this country is 5.5 kilograms. And there is a standard deviation of 0.5. What does that mean? I've drawn the mean in the center here. Look at the mean here. So the mean here is that 5.5. Okay, that is what you have down here. You have 5.5. Okay, now there is a standard deviation. That is a deviation from the mean. And you have been told that it deviates from the mean of 5.5. The deviation is always 0.5. So 0.5 above the 5.5 will be 6. Another 0.5 above the 6 will be 6.5. Another 0.5 above the 6.5 will be 7. And then on and on and on and on and on. The 0.5 below the 5.5 is 5. The 0.5 below the 5 is 4.5. And then you keep going on and on and on and on and on. So that's what I've just shown here. Now, suppose, according to the rule of large numbers, we call it the central limit theorem. According to the rule for normal distributed data, Once you have created this rising standard deviation, the rule, and the rule is called 68%. That's a beautiful name. I'm going to show you the rule right now. So the rule is called 68, 95, 99.7 rule. Okay, I'm going to come to that. The rule says that as long as your information data is normally distributed, then that's cool, that's okay. As long as it's normally distributed, then 68% of the data will be 1 standard deviation from the mean. Okay, in this context, it will be 1 standard deviation from the mean. What do we mean by that? What it means is that when you come to the very center, okay, of the population, and you have computed 1 standard deviation, that is, let's say 0.5 away from the 5.5 and 0.5 away leftward, that standard deviation, that deviation from the center is going to be 68% from the center. 2 standard deviations away from the center, left or right, is going to be 95%. And then 3 standard deviations away from the center, left and right. When I say 2 or 3 standard deviations from the center, this is what I mean, just so. So from here to here is, let's assume from here to here is 0.5. Okay, it's 0.5. And then from here to here is also 0.5. So when you add up 0.5 to 0.5 together, it's like you got 1. So it becomes 1 standard deviation away from the center. Okay. Then when this one is also 0.5. So if you add this 0.5 to this, you get 1. And then when you add, this is also 0.5. So when you add up 0.5 to this 0.5, you get 1. So the 2 of them becomes 2. So 2 standard deviation away from the center becomes that 95%. So what it means is that 68% of the data are in that section. In this very section, I have split into that. 68% of the data are there. Then between this one and this one, 95% of the data are there. And then the 3 standard deviation between here and that number, okay, and this number, 97.5% of the data are in there, which means that majority of the data are within the normal distribution. Very few, of course, remember this one goes to infinity. Very few are as you go further to the extremes. So majority of the data are in the center. That's what it's trying to say. Okay. Now, that rule is an important rule, which you shall see later on. So all that I said is here. Okay. So as you move away from the center, you are able to achieve 68%, 95%, and 99.7% of the data from 1, 2, and 3 standard deviation away from the center. Okay, so what are we going to do today? Having understood all of this preamble, this is what you are going to do. If I tell you to tell me the area I have shaded here, how will you tell me the area? Well, you should know that the area under the normal curve is 1. So if I want to know this very area shaded, all I need to do is to find this little area and then add it to what number? Who can tell me? I will get that little area here and then I will add it to what number? Let me see whether some of you are talking. What number will I add it to? Okay, somebody has written 0.5. Excellent. Solomon, Princess, Francis, Rita, Joanna. You add it to 0.5, and then you will know the area. So your only trouble now is to find this little area. Now, how do you find this little area? You will use, now remember that little area is going to be the X value. So you convert your entire analysis to a Z value, and then you convert the Z value to a probability. How do you get that little area? You get that little area by starting from the center and moving to the right. You will get the area. Then you will add that area to 0.5, and then you will now get your final answer. Okay, let's go to the second one. How do you get the shaded area? Who can tell me? Who can guess? How do you find the second? I'm not saying find it, but how do you find it? Okay, let me unmute one of you to tell me. Okay. How do you find the area? Well, the 10 is going to pause. It's going to pause. So let me give some few. Okay. Judith, I think you can give me the answer. Judith, try.
Please, I raised my hand for the question before, but I think to find the A area, you have to find the area, find it. So you just find the area with the Z, with the table, and then subtract it from 0.5, sorry.
Okay, good. You find this green area and subtract it, but how do you find it? This is my question. How do you find it? We'll come to that, by the way, don't worry. But you can ask your question now. Or you didn't have a question? Yes, someone. Someone, I thought you raised your hand, right?
So to find it, yes. So to find the area, the shaded area, it is 0.5 minus the area, which can be represented by maybe A. So 0.5 minus A will give you the shaded area. That's my answer.
All right. So one thing you guys want to note, you're right, very fine, is that when you are finding this area, you can't find that area first. You need to find this area first. I want to repeat. When you want to find that, shaded area, you cannot find that directly because whatever you're going to calculate is going to give you the white area. Remember, you always start from the center and then you move to the right, okay, or you move to the left. So you would rather find this area. Once you have found this area, then you subtract whatever you found from 0.5 to get that area, to get the shaded area. Okay, fantastic. Now let's go to the last one. So this last one, who can tell me, how do you find it? This last one. How do you find it? Okay. I got some answers here. The last one. So the last one, you will find this area to the right, and then you find the area to the left, and then you add them. Remember the way I'm showing the arrow. You find the area to the right, you find the area to the left, and then you add them because whatever area you find, when I say area, I mean probability. You find that, then you add them, and then you get your total. So that means that you are finding, sometimes we write it as probability of, let's say the first one is X. So the probability is going to be X A minus the random variable, okay, less or equal to the second one, which is in this case B. So you will find the probability, of getting an A, you will add it to the probability of getting a B. Okay. And that is because of the table we are going to use. Sometimes it will be different because of the table that another person uses. And then you add the two together. And then you can find it. Okay. So enough of all this. The next one is to just show a practical example. I'm going to use this simple one. So let's take this practical example, and I want you to work along with me. Ugas is a furniture company, and they sell furniture and carpets. We all know bogus. And from years of sales record, management has found that the mean number of yards of carpet demanded by customers, usually during a week, remember, they have found this over the years, that the mean number of yards of carpet is 4,200 yards, with a standard deviation of 1,400 yards. There is no sample size given here. Okay, we have not collected a sample here. We know from historical record that every week, the demand for carpet is usually 4,200 with a deviation of 1,004. The manager now wants to know the probability. Now, how do you know that this is a normal distribution? It's simple, because we have been given the mean and the standard deviation. We are being given, we are not calculating, we've been given the mean, we've been given the standard deviation from historical account. And now you are being asked that if the manager, if you want to know how much of carpet to be demanded next week, what is the probability that that carpet will exceed 6,000 yards? Remember, on average, you do get 4,200 yards with that bit of deviation. What is the probability that you're going to get 6,000 yards? How do you proceed with analyzing this? The first and the most important thing you want to do is to draw the information. You see, when you draw the information, it is beautiful. So let's try to make sense on how we can draw this whole information. How do you draw it? Okay, someone has asked the question, why do we find the area to the right first? Oh, you can find the area to the left first, Gladys. Okay, you can find the area to the left first and find the area to the right second. There's no criteria. All right, so the first thing is to draw, and I'm guiding you because once you're able to draw, you can find it. So I'm going to do this one with you. Just draw a normal distribution like this. I want it to look a bit nicer, because sometimes you guys, yours are nicer. So I want it to be a bit nicer. So let me draw this. So you draw a normal distribution, something like that. You go this way and then you show that way. Okay, I need to draw it again because I need a bit of space. And I don't want to use a blackboard because if I use a blackboard, sometimes the machine has a problem. Okay, so you do this. And you have the mean. You were told that the mean is what value? 1,004. So you can write mu equal to, sorry, 4,200. Okay, 4,200. And then the standard deviation. So you can write sigma equal to 1,400. So that's the first thing you will do. And then you are told that you want to know the probability that okay, demand for carpet will exceed 6,000. You are going to draw that. Now, so the first thing you ask yourself is 6,000, is it to the right of the mean or to the left of the mean? That's what you do. You can tell me. Is it to the right R or left? Or you can type the answer for me. Please get used to typing some of these answers, yeah? Get used to typing. Okay? Some of them I will allow you to talk, but some of them just get used to typing because you got to participate in your own rescue. Beautiful. So it is to the right. So now that you know it is to the right, you now go and then show that right. So you now go here and just indicate that right point. And that point, you now have to write the name. Okay. My place is smaller, but I'm going to still write it. So this point here is going to be 6,000. 6,000. Now, what is 6,000? If we were to use a letter, a symbol for this 6,000, what letter would we use? Who can tell me? Suppose we were to use a letter a symbol. Based on the entire knowledge we have been learning, what letter will you use? What letter will you call it? X, P. Someone says P, someone says X, someone says X bar. Okay, which one? Which one? Write some. I want you to type yours there. Don't worry if you fail. Okay, failure sometimes can be good. It will be a stepping stone. Okay, is it X? Is it mu? Is it sigma? Is it X bar or is it P? Okay, most of you are right. It is X. So we are picking a particular random variable, and that random variable is X here. So what is the probability that demand for carpet will exceed 6,000? Remember that he did not ask you what is the probability that demand for carpet will be 6,000. I rather said will exceed 6,000. So given that the mean is the center here, where are we going to shade? Let me give some letters. Are we going to shade the area of A, or B, or C? Where are we going to shade to represent demand for carpet will exceed 6,000? We are going to shade C. That's it. Okay. So you got to learn how to do this thing. So you shade this C. So you shade this area. So this is the area we are looking for. That is the percentage. That is the probability that we are looking for. We are looking for that area. Beautiful. The first thing you have to do is to use the X they have given you, the 6,000, to find its equivalent Z value. Remember, we need to standardize the whole thing because 4,200 is too wide. So let's standardize it. How do you do that? You will write the Z formula. The Z formula is given by X minus mu over the sigma. X is 6,000. So you get 6,000 minus the mu. The mean is what? 4,200 divided by the standard deviation, which is 1,004. So you take your calculator and then you tell me the answer. Please tell me the answer. I want you to participate in your rescue. You can tell me the answer to that. Be part of the whole preparation. Be part of it. I could tell you the answer, but I want you to tell me. Please be careful with the answer you give because your answer should always be 2 decimal places. And I've seen that some of you are giving an answer which is wrong because it's not in 2 decimal places. Aha. All right. So the right answer is 1.29. 2 decimal, not 1.28, 1.29. Now you know the Z equivalent of the value that you're having. So what does that mean? Remember we said that the mean is 0. So at this point, we have here 0. So the 4,200 corresponds to 0. And to the right, that number here is 1.29. That is the number there. Remember the 1.29 is at the edge. It's at the edge. It's not the above, it's at the edge. Okay. Now, how do you find the area that exceeds 6,000? Now that you have the 1.29, you have to go to the Z table. But please watch something. Watch something. The Z table we are going to use here. The Z table is going to give you the area which is from the center, okay, to the right. That's what it's going to do. It's going to give you this area from the center to the right, from the center to the right until it gets to that 1.29 section, which is the 6,000. It's rather going to give you that area. When whatever you get there, you will now subtract it from 0.5, and then you'll get the actual area, which is the exceed part. All right. So how do you get to this? You have to go to the Z table. Okay. So let's go to the Z table.